In a previous video for 9b, we looked at differentiation patterns for polynomials. In this video, we're going to evaluate derivatives at a point, which means we're actually going to be finding the gradient of the tangent at a particular point. We're going to look at the formula m equals tan theta, and we're going to relate it to the gradient of the tangent at that point. And then finally, we're going to look at the relationship between strictly increasing or decreasing functions and derivatives. Also in this exercise, you'll come across questions where you have to recognise that if you evaluate the derivative at a particular point, you'll get the gradient of the tangent line at that point as well. So you'll get two sorts of problems. One where it asks you to find the derivative, and the second at a particular point, or find the gradient. The other sort of question that you get is, given the derivative, find the point on the curve, or given the gradient of the tangent, find the point on the curve that has that particular gradient. So here's an example of that sort of question. So for f of x is 2x cubed plus 5x squared, find. Now all of these four options are asking you to do exactly the same thing. So it says find the derivative when x is equal to 2. Find the gradient of the tangent, which is just the derivative. That's the derivative. Find the derivative at x is equal to 2. So we've got x is equal to 2. We've got at the point 2. We've got find the rate of change. The rate of change is the derivative. And again, we've got when x is equal to 2. And find the rate of change at the point 236. So they're all actually asking us to do the same thing. And what they want us to do is to find the derivative. So f dashed of x is equal to 6x squared plus 10x, and then evaluate that at x is equal to 2. So f dashed of 2 is equal to 6 times 2 squared plus 10 times 2, which is equal to 44. So the other sort of question was the one that asks us to find the points, and not just find the points, find the coordinates of the point. Okay. So the question tells us that the gradient is 9. That means that our derivative is 9. So our equation is in the form of y is equal to x cubed. So our derivative is going to be dy dx. And dy dx is going to be 3x squared. And we're told that 3x squared is equal to 9. And so what we have now is an equation that we can solve to find the x coordinate of the point. So divide both sides by 3, square root both sides, and you'll get x is equal to plus and minus the square root of 3. So we've actually got 2 points here, one with an x value of root 3 and the other with an x value of negative root 3. So we'll need to substitute both of those values into our function. And when you substitute in root 3, you get root 3 cubed, which is root 3 times root 3 times root 3. And root 3 times root 3 is 3. And negative root 3 cubed is negative 3 root 3. And I just wanted to, you can see the screenshot from the CAS calculator over here, and I just wanted to show you how you would go about doing this on your CAS calculator. You can actually put into your CAS calculator that you want it to solve a derivative equal to a particular value. Can you see I've made the derivative of the function equal to 9 and then asked it to solve that derivative for x, which is what it's done. And it's given me the two answers here. And then what I've done is I've taken those two answers, and because I defined my function first of all, I could just substitute those answers straight in. So I used these curly brackets here, which you'll find here on your CAS calculator, and I just copied and pasted that down, copied and pasted this into here, and then cleared it out, and it's given me the two answers that I got before. One of which is wrong because I forgot a negative there. So there you go, now I've fixed it. The other thing that you'll work with in this exercise is the equation m equals tan theta, and you need to understand its relationship to the derivative and also the gradient of the tangent. So that you can see that I've drawn a curve here, a point with a tangent, and you can see that the tangent is actually making an angle with the positive arm of the x-axis. Can you see it there? And that's the theta that we're talking about in tan of theta. And here's a blown up version of it. And so how is the gradient of the tangent related to that particular angle there? So if we look at our right angled triangle that we have there, that goes this way here, there's two things that we can use this triangle for. One is to calculate the gradient of the green line, which is using the rise, this distance here. We call the rise over the run, that distance there. Or we can take exactly the same triangle and look at it in terms of a right-angled triangle, and this side is the opposite, this side is the adjacent, and we have the relationship that opposite over adjacent is tan theta. And so if we connect the two together, our opposite side is in fact our rise, and our adjacent side is in fact our run. And so we can rewrite the formula for tan theta as being rise over run, which is our gradient for our tangent. So the gradient of the tangent is equal to tan of the angle that the line makes, the tangent line makes, measured in a positive direction from the x-axis. So that means even if our tangent touches the x-axis in a different quadrant down in the negative section of the graph, such as the one here, the angle is still measured from the positive, in a positive direction from the x-axis. This one here, positive direction of the x-axis, so we're still measuring it in this direction here. So the sorts of questions you get with this are again two types. First, find the coordinates of the point that fit the requirement, and then the second one, work out the angle. So let's look at this first one. Find the coordinates of the point on the curve y is equal to x squared, at which the tangent makes an angle of 45 degrees with the positive direction of the x-axis. Okay, so we know that the formula is that the gradient of the tangent m is tan theta. So m is the gradient of our tangent, which we know is the derivative of the function. And so the derivative of the function, our function is x squared, so its derivative is 2x. So what we have here, and we know that the angle is 45 degrees, it says so in the question. So what we have here is that 2x is equal to tan of 45 degrees. And tan of 45 degrees is 1. And so we have that 2x is equal to 1 and that x is equal to a half. But we had to find the coordinates of the point, and so we're going to have to substitute a half back into the equation. And so we have y is equal to a half squared, which is a quarter. So our point is the point 1/2, 1/4. So that's an example of find the coordinates. The second sort of example is to find the angle. So here's an example here. So this example says, find the angle that the curve y equals 3x squared minus x makes with the positive direction of the x-axis at 0, 0. Okay, so we know that the gradient of the tangent is tan of theta, and that theta is the angle with the positive direction of the x-axis. We know that this m is the gradient of the tangent, and we also know that the gradient of the tangent is the derivative of the function at that particular point. And the point we're working with is 0, 0. So let's find dy dx at x is equal to 0. So what we need to do is to find dy dx, which we do by differentiating our equation for y, and we'll get 6x minus 1. At x is equal to 0, we substitute in a 0 for our x in dy dx, and we get dy dx is equal to minus 1. And so we can put that together with our formula for tan theta. And so we have that minus 1 is tan theta. So to get theta, we take the inverse tan of both sides, and we end up with inverse tan of 1 is equal to theta. Now when we do that on our CAS calculator, or on any calculator in fact, this section here on our CAS will tell us that it's minus 45 degrees, or that it's negative pi on 4. And that's because if you remember our work on our inverse functions, tan only exists in the first quadrant and the second quadrant, the first quadrant and the fourth quadrant. So what we've actually got here is a line that's sloping with a negative slope, and our calculator is telling us that the angle is actually minus 45. But what we're asked to find is the angle that is from the positive direction. So we're actually asked to find that angle in there. That's our theta in there. And so the green line makes a straight line. The green line is a straight line. So this angle adds to 180 degrees. So this angle in here is 135 degrees. And so our theta is 135 degrees. And the final thing to look at is the sign of the derivative and the shape of the curve. So you can see I've got a curve there, and at the two turning points I have that the derivative is equal to 0. And to the left of A in this section, the graph is increasing and it has a positive gradient. It also has a positive gradient to the right-hand side of B. So it has a positive gradient for x less than A and x greater than B. The bit in the middle between A and B, it's a decreasing graph. And so between A and B, our gradient is negative. Now I've used the word increasing and decreasing there to describe the shape of the function, but please don't be sucked into thinking that the derivative, you can use the derivative of the function to determine whether a function is increasing or decreasing. Let's have a look at the graph of x cubed. So here's the graph of x cubed, And this is the graph of a strictly increasing function, even though it has a derivative equal to 0. And this is the graph of y equals negative x cubed. It's a strictly decreasing function, even though it contains a point where the derivative is equal to 0. So what this means is that if a function is described as being strictly increasing or strictly decreasing, it does not imply that the gradient is positive or negative over that whole interval.